Today we are going to discuss the application of dynamic programming with MDP in reinforcement learning. Application of dynamic programming in Markov decision process with Markov decision process in reinforcement learning. As we know, the reinforcement learning is a learning process, is an advanced machine learning process where we have the states, we have actions, and we have the the various uh, policies from a particular state. If you take the certain action, it has to be transited to the next state, and some reward will be earned. And the reward can be maximized to get the final to get the optimized uh, score, what is called the value function, or we can say action value function or whatsoever. So finally, gradually improving and gradually optimizing the training process is a main essence of the reinforcement learning. So it is all about earning the rewards, maximizing the rewards. This means actually maximizing the perfection, the maximizing the accuracy of the training itself. Now, see, before starting the MDP and the dynamic programming, let's go into the insight of the state value function, or what we can say that the state value function and the action value function. And what is states, what is action, what is the state value function, what is action value functions. And those are very, very required to have a deep insight. Now, now state value function. Firstly, the state value function is a quantitative measure, is a mathematical equation, the mathematical function that represents the value function of a particular state. Agent staying on a particular state can take innumerable number of actions, can any action, okay, and that lead to different next states, different next states. The state value function is a potentiality or the capability of transition to the new next states, okay, for by taking any available action, by taking all available action, what is the best outcome the agent can have by staying at the current state, the best next state the agent can reach by staying in the current state. Okay, whatever the best action the agent can take, and that defines the state value for whatever the best act. By taking the best action, the agent can arrive to the best uh, possible next state, and that is the state value function of the current state. That is, we can say, the potentiality, the maximum potentiality of the current state. Action value function is also a value function that is action specific. Staying in a current state, given a particular action, by taking a particular action, what is the maximum, what is the state that the agent can arrive? What is the best state the agent can arrive in the next state? Okay. In the next stage, what is the best state the agent can arrive? That is the action value function. Here, the state and action both are given. A combination, a specific combination of state and action by which the agent can arrive the best next state. And that is the action value function, or we can say often the Q function. These are the essential components of reinforcement learning. Those both, actually, both of them actually are measuring the quality of states and action under a certain policy. Where the policy we know is a combination of state action reward and the state action reward, and also it includes the transition probability and the final these functions. Now see what we have, the state value function. The definition, the mathematical definition is very precise here, that the value function of under a certain policy pi, the value function v pi s, v to the power pi, it is actually not to the power, it is actually superscripted pi. That means a policy v value function under a certain policy of a current state s. What is the potentiality of s? What is the value of s? What is the value that represents the potentiality of s under a certain policy pi, that is v pi s? is equal to expectation, expectation parameter, that is E. Expectation parameter, G means the return, the goal, the return. Okay. At certain point of time T, and st equal to a, at a certain point of time T, what is the state? And that is actually the current state, small s. So actually the meaning and interpretation of this is the expected return, the expected return of the return of the agent when the agent stays at the current state S. Or we can say the expected potentiality or expected best return or best expected potentiality of the agent when it stays at the current state small s. So that is the interpretation of this first line, the definition, the precise definition. Now the Bellman equation. The Bellman equation comes to the recursive relationship, or it can be represented iterative operation also. It can represent it by it is actually a recurrence relation or recursive relation. The Bellman equation states that value function under a certain policy pi is equal to the summation of all actions, summation over all actions where I a given s. Actually, under a policy, this is a transition probability what we can have. This is a transition probability pi a bar s. That is a conditional probability, which is a transition probability. Okay, what we have, or there's an action probability what we can have. The action that the probability of action to be taken when we stay at the current state S. The probability of the action A to be taken when we are standing on the current state S. So there's the action probability. The probability of taking action A. Okay. First of all, the summation will be done. The sigma is done over all the actions. The sigma is done over all the actions. And we have the pi A given S. That is the probability of the action given the current state S. And the summation over all next states. S prime is the next state. All possible next states when we have a specific state and action pair for a particular next state and action pair, we employ a specific fixed state action pair and we are going to the S prime, that is the next state, multiplied by the current reward, that is from current state S to the next state S prime. When we have transition, we by taking action A, we are earning the reward R by having a transition from current state S to the next state S prime by taking action A, plus the discounted value of the value function, the discounted value of the expected value function or future value function for the next state, for the next state S prime. So this R S comma A comma S prime, that is a reward function as a function of current state action next state, plus the discount, gamma is a discount factor as we can see, and V by S means S prime. That means the value function of the next state, the value function of the next potentiality of the next state, or we can say the quality of the next state under a policy pi, this total thing that is R plus gamma into V by S prime, that whole thing represents the total reward or total return up to the next state, including the current state as well as the next state. So the total return of current state as well as the next state multiplied by the probability of the next state itself is prime. What is the probability itself that we are going to the agent is having the transition to S prime? The actually the product, the result of this multiplication is the likelihood of the return that the agent is going to earn when it has the transition from state S to S prime. Because this is a total potential reward what we have framed here, we presented here, RSA S prime plus gamma into V by S prime, that is a total reward from next state and current state and the next state, taking together, multiplied by the probability. That means possibility itself to have a transition to the next state is prime. So the product itself is actually likelihood of having a transition to having a total reward till the next state is prime. And this is only for one S prime, one next state, and the return will be that particular total return that will be summed, that will be actually having the added, all the returns will be added for all next states. All next states. S prime is not one state. S prime is an instance of next state. So for all S primes, all next states, we are adding up the returns. The current state plus next state, the total return for the current state and next state together. So we are adding up all the returns if we have the for all next states S prime multiplied by, now we have this thing multiplied with the probability of action when we have the current state is. When the agent is standing on the current state is, what is the probability that the action is taken? Now we are adding up all these action probabilities. So probability of the action. So for all over all states, first of all, for a given state and action pair, we are having a transition to next state is prime, and we are adding up all the probability, all the total potential rewards or potential return when we have the transition to any next state. All the next states potential returns are added here. That means the for a specific state and action pair, and what is the total reward that we are going to get. There's a total potentiality for a specific state action pair. And this is for one action, only for state and action, on a given state and action, for single state, current state, and single current action. And that particular value, that will be that will be multiplied, weighted by this probability, conditional probabilistic measure that we have the by A given S. That is the transition, the action probability, the probability the action A is chosen given the current state S. Given the agent is on current state S, what is the probability action A is chosen? Okay. So we are saying about the action A and state S, this is fixed. And the probability multiplied by this conditional probability will represent the likelihood of the action itself is taken. Okay. And the total product represents now when we are having state S, when the agent is standing on state X, when we have the state S as a current state, and we take action A as the action to be chosen, then what is the total return that we expect? And that will be added for all actions. Now actions are varied. For different actions, we have this product, and we are adding all these for different actions. So the matter comes here. It is representing the sum. It is representing the sum of returns, the sum of total returns for all actions when the agent is standing on the current state S. So this is a value function or the potentiality of current state. From current state, whichever actions are possible, for all actions, if we sum up the total returns, so that means the grand total of return by considering all possible actions the agent can take will represent the value function that of the current state S. So this is the first Bellman equation. We have the value function. Similarly, we have the uh, same method by which we can derive the action value function, or what we can say the Q function. The definition is very simple. Basic definition that Q function or action value function. The Q value or the action value is a function of state and action both for a certain current state and for certain action for a fixed current state and the fixed action A. What we have, what is the total potentiality of the agent? Okay, to go into the beta state. So the Q value is the value function or action value function is the value function that is based on the given state and action, given current state and action. When the current state and action is given, what is the potentiality that the current state, what is that the agent is having, given the current state and action, not only the current state, but current state action both are given. Okay. For a specific current state and specific action, the agent can take, and that leads to the whatever whatever best solution the agent can, whatever best outcome the agent can have, that is represented by the Q function or action value function equal to expectation of the return for a specific current state S and specific action to be taken A. So Q function is for a state action pair and value function V, that is for state only. For value function is computed for all actions together, and a Q function or action value function is only for a particular state and particular action. Now, the recursive relation of Bellman equation for the Q function or action value function is equal to the Q pi SA, that is the Q function or the action value function under a certain policy pi as a function of state and action is equal to the sum over all the next states. The sum over all the next states, the probability of the next state, the probability of the next state given the current state and action. When the current state and action is given, what is the probability that the agent will have a transition to the next state? That is called the transition probability. That is called the transition probability. Previously, we had the action probability and transition probability both. Suppose this pi AS in the previous equation, the value function, this is called the action probability. The probability that the action A is chosen given the current states S. And this is called the transition probability. First one is the action probability, and this is the transition probability. What is the probability that the agent will have a transition to S prime given the current state and action as S and A? Given the current state and action. Okay. So these are the very key concepts to analyze all these things. Now we have the transition probabilities of the agent to the next state S prime multiplied by the reward, current reward for after transiting from current state S to next state S prime by taking action A plus comma the discounted value of the discounted value of the total, the sum of all the returns, actually the sum of all the returns we have, the Q value, the potentiality of the next state and next action, the potentiality of the agent for next state and next action. In the next state and next action is given, what is the potentiality that represented by the action value function Q by S prime A prime, multiplied by the probability that the next action A prime will at all be chosen. So this product actually represents, this product, the product actually represents the value of whatever value we can assume, whatever Q value we can assume for the next state and action. If I assume the next state and action S prime and A prime is given, then how much potential value we can consider for that state action pair S prime A prime. So this is actually added for all next actions, all actions to be taken. A prime is action to be taken, future action, next action. So it is for all next actions, all future actions, we are adding up this value, this estimated value. So that will actually represent for all actions, this is a value function. This is a value function. This is a value function of the future state, that is S prime, the next state, the value function of the next state. So it is actually recursive. The, the Q value of the current state and action pair is equal to, we are adding up the probability of the agent to have a transition to the next state multiplied by the current reward plus the discounted value of the next state's value function. This whole thing is the next state's value function. This is the total potential reward, the total potential return till the next state, to the next state, till the next state arrives, multiplied the probability of the next state. At all, what is the probability that at all the agent will have a transition to the next state? So this product will again be representing the, the actual value to be considered to be generated for the next state or expected value. Okay, when we weighting something by the probability, it becomes expectation. So this is the expected value, what we have here, the expected return of the next state. So expected return of the next state when we have the state and action as given, the current state and action is given. Now this is for all next states. We are adding up for all, not only one next state, for all next states. So we are getting the total value to be generated by the agent, the total value to be generated by the agent. If the agent is standing on state S and taking action A, when a state is fixed, current state is fixed, and the action is fixed, then what is the total potentiality of the agent? The total potentiality, this means the total, the action value function, but that we can, that the agent can achieve. That is called the Q value function of AC, current state is and current action A. Those two are given. For all states, we have to add the, the expected return to be considered. Expected return because it's weighted by the probability itself. So expected return for a certain state will be added for all states, all next states. For a certain next state is prime, this is the expected return. And this is for all next states, we are adding up the same thing. So this is actually the Q function or action value function for the current state and current action, both. Previously, we have the value function of the current state only. Taking all the actions together, that's why there is a summation over all actions. Finally, there was a summation over all actions. But here we are having a particular state and action, so we should not go for the actions now. Action is given, state is given, so we are adding up only the states. For all the next states, this total value will be added. The probability that the agent is having a transition to S prime, given the agent is standing on the current state S and taking action A, multiplied by the current reward plus the discounted value of the total return for all actions for the next state and next action. For all possible next actions by standing on the next state. Whatever the value to be generated, that is the future value function or the value function for the next state multiplied by the discount factor gamma. As we know, any future return, any future expected return can be discounted to represent for the current state. Okay, to represent any future return in terms of the current state or current phase, we have to discount it by the discount factor by multiplying the discount factor. The gamma is a discount factor, typically lies between 0 and 1. And the value of gamma determines that how much weight the agent has to make, or there is a waiting time for the next state. What is the span of waiting? What is the length of waiting time for the till the next state comes? Okay, that is determined by the value of gamma. If the interval between the current state and next state is too high, then the value of gamma is definitely the value of gamma is too low, is lower. Higher value of gamma means the next state will come very fast after the current state. And the duration is the gap, the interval is not that much. So the gamma basically represents the gap between the current state and next state, the time gap. So this discounted value of the value function of the next state plus the current reward, this means, again, I'm telling, this means the total reward, a total return that the agent is expecting till the next state, current state and next state together, multiplied by the probability is the total expected return considering current state as well as the next state. Current state and next state's total return multiplied by the probability that the agent will have a transition at all to next state S prime. Okay, if it is having the transition to X prime, then what is the expected total return? That is the thing. That is R S S prime plus gamma into summation A prime by A prime given S prime multiplied by Q of pi S prime A prime. That total thing is the expected return, total return, if the agent is having a transition to the next state S prime. Now multiplied by the probability that the agent is having a transition at all to the next state. That is probability of S prime given SA. Given state and action pair, current state and action pair, what is the probability that the agent is having a transition to S prime? So the total thing, the total product, this product, this multiplication represents the the value. The value we have to assign, the return, the value of the return to be assigned are considered for this particular state action pair. Now that is for added, that is for one state S prime, that is added for all next states S prime to get the Q value function or action value function for the current state and current action SA. If the agent is having a specific fixed state S and specific fixed action A, then Q of SA, that is a Q function, Q as a function of SA or Q function, or we can say action value function, actually represents the total expected outcome. The total expected outcome. Okay. So the probability, it is weighted by the conditional probability. This means the weighting by conditional probability is actually the weight factor. The probabilistic multiplier means the weight factor. It is weighted by the probability. If the probability is low, the weight factor is very low, so the total value will be less. And probability is more the probability, the weight factor will be higher. So this is the total potential value to be generated if the agent is standing on current state S and taking action A. Now let's have the relationship between them. The value function equal to summation over all actions, the action probability that we can say pi A given S, action probability that the agent is choosing action A by staying on current state S multiplied by the Q value as we have this one. So as a relationship between these things, so summation of all actions, we have the action probability, the probability the action is chosen, given the current state is multiplied by the Q value for a particular state action pair. So the Q value for a particular state action pair multiplied by the at all the action A is chosen, the probability that the action A is chosen at all. So this product actually represents the expected value to be generated by considering state S and action A. If the agent is having this current state S and action A, then Q value will be generated, and that is the probability that at all A is chosen as the action. So this total product, actually, the product of all these two components typically represents the value to be considered for this state action pair. And that is for all actions to be summed. And that becomes the value function. So this is the relationship between value function and the Q function, or value function of the state value function and the action value function. P pi is a state value function or simply value function. Q pi is A is an action value function or Q function. Or we have this particular thing that Q pi is A is equal to, similarly, we have the value function. We can analyze it again. The value function is equal to summation of all A, the action probability, pi of A given S, multiplied by this whole summation. That is a Q value actually. This internal, this thing, just pay attention to the mouse pointer, where the mouse pointer moves. This particular part, the summation of S prime of probability S prime given SA multiplied by the reward as a function of SA S prime plus the discounted value of the value function. This total thing, this total, the second part, the summation from the starting from the summation to the end, that is the value function of the current state. That is actually, we can say the Q function of the current state action pair. This is the Q function of the current state action pair, this total thing, because it assumes state and action pair as constant. The state is an action A as given or constant. It assumes. So it typically represents a Q function. So the Q function for a particular state action pair multiplied by the probability that the action A itself is chosen, and that estimate, that expected Q value that is added for all actions giving the value function under the policy pi. Similarly, we have the Q function. We have the Q function. The second part after gamma multiplied with gamma summation A prime summation over all actions. We are having the Q value for particular state action pair for the next state and next action is prime A prime multiplied by the next action is chosen. What is the probability that the next action is chosen? And that is summed over all the actions. So we have the Q value function, and this is the value function. So this is a relationship we can derive. The Q value function is equal to the summation over all S next states multiplied by the probability of S prime SA plus into the reward plus discounted value of the value function of the next state value function for the next state. Okay. So these are the relationship we can derive. Now we have the optimality equations, Millman optimality equations we have. So it is easily derived V prime V star S equal to. Now, optimal value, optimal state value and optimal action value, or we can say optimal V and optimal Q. Optimal state value function or optimal action value function or optimal Q value function. Okay, that is derived in this way. We are taking the maximum of this, maximum of summation S prime of probability of S prime given SA multiplied by the current reward plus discounted value of the optimal value function for the next state. This total, this total is calculated for all actions. For all actions. This is for one action, state action pair. This is for one state action pair. This summation part is a one state action pair. And this will be considered for all actions. And we are chasing the best one. We are choosing for all actions, we are choosing the action for which it gives the best value. Okay. What is the best value? What is the highest value? Maximum value by certain action. That maximum value is the optimal value function. That is the optimized value function. We have V star S of the current state S. What is the optimal value function for the current state S? Equal to the maximum of all the value functions, all the Q functions for all the actions, was all the actions available right now at the current state, and we are choosing the highest out of that. For n number of actions, we are deriving the Q functions. This is actually the internal one. The summation part is actually a Q function, as we have already discussed. The Q functions for all separate actions we have derived, and we are taking the best Q functions. Okay, for all actions, and we are taking the best out of that. That is the value function. Okay. So actually, for all actions we are adding up. So we are all actions we are having these value functions, this Q function, and we are taking the best one, the best action that gives the highest estimation of the value. So maximum of A, we are taking the maximum Q value, the optimal value function, state value function is equal to the highest Q value for a certain action. Okay. We will choose as a highest Q value. Now, the optimal Q value function or optimal action value function is equal to the summation over all the states. We are having the probability that the next state transition will be taken. Instance of the next state is prime here, multiplied by the potential return till the next state, that is a V star S prime is the potential return that we have, that we derive this one. Okay, gamma multiplied by, so this is the maximum of all the actions. This is again max of A prime. So we are taking the max of Q values for the next state action pair. We are choosing that action A prime, which will maximize this Q value for next state action pair. That is actually the value function for the next state, optimal value function for the next state. Discounted value, optimal value function for the next state, plus the current reward, multiply the probability of the transition probability for the next state, and that is added for all states, next states. That is added for all next states. That is the optimal Q value function or optimal action value function for all the next states. What is the potentiality of state action pair for all the next states? That is the Q value function of the current state action pair. Okay. Now we have the summary of these that we can easily see. Now the Markov decision process. Typically, the MDP or the Markov decision process is a state of states action, transition probabilities, reward, discount factor. Okay. The transition probability we have, the probability that the agent is having a transition to state S prime given state, current state S and current action A. Okay. The goal is find a policy pi that maximizes the cumulative reward. Okay. Now here, dynamic programming is typically a system where we solve optimization problem by breaking them into sub-problems. Now, it utilizes the Bellman equation because dynamic programming is something which dynamically update the value state value function and the action value function dynamically updated. And the same sub process that is repeated or reused again and again. Okay, the updation process itself, the update rules or Bellman update rule or Bellman update equation reaches to optimality by these recurrence operation that is, or we can say recursive operation, or also, or even it can be represented iteratively as well. So we can see, we can show that particular thing. That is Bellman equation. It utilizes the state value function, action value functions. Those are getting updated gradually till the optimal points are reached. Okay. Now, this is a dynamic, typical feature of dynamic programming, and that is applied on the framework of state action, transition probability, reward, discount factor, and the policy. So, this framework, SAPR, gamma, pi. So, this combination is called a, actually, this is represented as a MDP, Markov decision process in RL. So, this is uh, whenever dynamic programming principles are applied in the MDP model or MDP framework, then we have this state value function updation, the Bellman equation, the optimizing the state value function by Bellman equation, optimizing the action value function through Bellman equation, optimizing the policy. So we have this state value function. Okay, optimal state value function we can have. Optimal action value function we have already shown there. Okay, these equations actually form the basis of dynamic programming in RL. This is the exact example, the exact instance where dynamic programming is used in RL. Okay, because the value function, the optimal value function, optimal state value function is gradually achieved for all states in the same component that is reused for the next state. Suppose V star S is equal to so and so, maximized the maximum of this thing for certain action, we are having the maximum of this value. That value itself is the sum of all the probabilities for all next states, the probability of the next state multiplied by the current reward plus the discounted value of the discounted value of the next state value function for the next state. This whole thing is called V star S. Similarly, we can, using the same formula or same update rule, we can derive V star S1 or S prime, the next state. Or by using the same formula, the same update rule, we can derive the V prime, V star S double prime, means next up next states. Then next up, next up, next states. In this way, we can derive the state value function for next states and subsequent all states by using the same update rule or the same equation. For action value function, also same thing. We can reuse the update rule for all state action pairs. For one specific state action pair, we are using this. For all state action pair, we can use the same way, the same update rule. So this is a typical feature of dynamic programming, which is reflected in Bellman equation in MDPs. So now this is the way we have dynamic programming algorithm for MDPs. The policy evaluation, as we have compute V pi S for given policy pi. So V pi S equal to pi into pi of A by S, that is the action probability. We are adding up all the action, probability of all the actions. For all actions, we are adding up this probability multiplied by the same thing, the sum of over all the next states, the probability that the next state is arrived multiplied by the return. If we arrive, if the agent arrives at the next state, plus the potential, the value function, the the discounted value of the value function under the policy pi when the agent is having arriving in the next state S prime. Okay. Plus the reward, current reward, immediate reward that the agent earns when it has a transition to the next state S prime, plus the value function at the next state is prime discounted by gamma. See, the total is the total expected return, the total estimated return for the current state and next state together, multiplied by the probability that represents at all the agent is having a transition to the next state if the agent is standing on its current state and taking action A. That is added for all the next states, multiplied by the the action to be taken at all the action A is chosen, the probability at all the action A is chosen if the agent is standing on state is current state is, and that is even the total product is now finally is added for all actions except this outer summation. This is actually the Q function. This is actually the Q function for a particular action state pair. For particular current state action pair, this internal summation is the Q value function. External is a value function. Now, policy improvement, we will choose from the policy, okay, the value function, the state value function under a certain policy. We will choose that one. We will choose the action. The action will be chosen that will maximize the internal. That is the summation over all S prime probability that the transition to the S prime multiplied by the immediate reward plus the discounted value of the next state. That is actually the highest. That is what we can say this is a Q value. Again, we are having the Q value. The summation of this internal summation is a Q value. So we are choosing that action which will maximize the summation part. That means we will choose that action A that maximizes this Q value. That is summation over the summation of all the next state S prime, the summation of all the next state S prime, that probability that at all the agent is having a transition to S prime multiplied by the current immediate reward by transiting to S prime plus the discounted value of the value function for the in the next state. So this is the policy improvement. We are choosing the maximum one. We are choosing that action in the policy. The policy includes that action that will maximize the Q value. So in simple word, the policy includes that action that as an optimal action that will maximize the Q value. Now, policy iteration, the policy evaluation and the policy improvement together actually constitutes the policy iteration. So, and the value iteration is just like that. We have, we have, we are getting the maximized Q value as per the Bellman equation. The same thing represented as the value iteration. Okay. So, maximized Q value for a certain action where maximized Q value is the value function. And the policy iteration includes the action itself. The value iteration includes the, the value iteration actually selects the highest value for a certain action, the highest Q value for certain action. For all actions, the Q values are derived. It is choosing the highest Q value for certain action. And the policy iteration chooses the action as the optimal one. Optimal action is chosen that will maximize the Q value. Okay. So these are the various application of dynamic programming in reinforcement learning in accordance with MDP. Okay. The limitations of DP in reinforcement learning, there are scalability, model dependency. There are the various limitations are there, shortcomings are there. Okay, the transition model should be known. First of all, in dynamic programming, assume that MDP, the Markov decision process, the MDP is given. It assumes that MDP is true. The MDP, whatever MDP is given, it assumes that as a fact, as a known fact. And that may not happen always. Okay, transition probability is also given in case of dynamic programming. Dynamic programming considers that transition probabilities are given, but transition probabilities may not be given, and highly probable that they are not given. Transition probabilities are can be derived again in other ways. So this transition probability, the probability that the next state will arrive, the agent will arrive to the next state, given the current state S and action A, that is given for all the next states. In the dynamic programming assumes these transition probabilities to be given for all the states, and which may not be the reality in maximum cases. Scalability is also a problem. Okay, thank you so much. So the next video will explore the further advanced concept based on this. Thank you.